Welcome to the continuing education course sponsored by the Structural Insulated Panel Association. This course is titled Commercial Design with Structural Insulated Panels. My name is Al Cobb, and I will be your host and delivering the audio portion of this one-hour program. My background in the structural insulated panel industry is one of both manufacturer as well as past president of the association. I have worked in all facets of the industry, including manufacturing, installation, training, engineering, design, as well as sales. I am the founder and owner of the SIPS school located outside of Washington, D.C. in West Virginia. I also, through that organization, provide training and consulting, both domestically and internationally, to assist people in setting up structural insulated panel manufacturing as well as projects. Over the next hour or so, I hope to impart some of my wisdom as it relates to my 26-year history in the structural insulated panel industry and help you better understand how SIPS can be used in commercial design to create and provide high-performing buildings in the built environment. Let's move to the boilerplate information as it relates to the American Institute of Architects and their continuing education program. Not only is this program registered with the AIA for continuing education, but it also seeks to deliver unbiased information. This is not for marketing purposes. This is merely to help provide education as it relates to SIPS. The format of this course is not live. It is going to be online, and of course I am providing the audio portion of this. It is for one credit under health, safety, and welfare for continuing education. This course is scheduled for 1 hour. The outline of the course is in front of you. What we will attempt to do here is provide you with some general understanding of SIP basics. We'll get into some of the engineering methods as well as you can see, sound and fire ratings. A lot of what we'll talk about is code compliance, the interaction of both structural systems and other types of systems that interrelate to the envelope or the SIP envelope. We'll talk briefly about life cycle analysis. A lot of what SIPS is about is the thermal characteristics and how they meet the codes and how they can provide a thermal envelope which performs much higher than some of the other competing systems. We're going to talk a little bit about the climate specifics and how those climatic conditions will change the detailing of SIPS and how you should detail buildings differently, obviously, in one climate zone versus the other. We'll touch briefly on indoor air quality, and of course we'll go over construction methods and specifications as we start to wrap up this presentation. The objectives of this course will be such that you as a design professional at the conclusion of this course will be able to deliver some basic information about SIPs and their use. This would include both their composition, how they're made up, how they're applicable to codes and standards, additionally identifying the energy efficient characteristics of the SIPs and how they can improve overall building efficiency, a good understanding of waste reduction and how the life cycle analysis benefits to building with SIPs, as well as how it relates to traditional wood framing. And of course, understanding how SIPs contribute to better indoor air quality by reducing air infiltration, as well as controlling any off-gassing issues. So let's get right into it. What is a SIP? Let's start with the basics. What does a SIP look like? What's it made of? In essence, it's a composite structure. It's very simply, in most cases, 3 elements. It's a skin, a piece of wood glued to a foam core. The skin is on both sides. It has to be on both sides because this is what gives it its structural integrity. It is as a composite structure, the rigid foam core is predominantly expanded polystyrene. That's EPS, or the white foam, similar to you see in the photo. In addition, it could be XPS, or extruded polystyrene. This would be the foam that might be referred to as styrofoam, or the foam that might be extruded that would be green. So you might see a colored foam, green or blue. The other option could be polyurethane. Polyurethane is delivered a little bit differently, and we'll talk about that later on. The structural facings, if we are going to use a structural facing and create a structural panel, will usually be 7/16 exposure 1 rated OSB. And of course, the adhesive is structural in nature. It's very similar to the engineering grade structural adhesives that you might find in a I-joist, glue-lam, Paralam, any of the other wood engineered products that you see so often in the marketplace. SIPs are not new. They've been around since the 30s. They were first developed by the Forest Products Laboratory up in Madison, Wisconsin. They were being researched in order to answer the question about eventually running out of wood. Even though it's one of our nation's greatest natural resources, it was determined that we needed to maximize the efficiency of that wood and come up with better ways to utilize it as we built buildings. And the methodology of taking that wood and turning it into oriented strands to create sheathing. Originally it was done with plywood. Now we're working predominantly with oriented strand board. And of course the foam cores were introduced later in the 60s. That technology, when expanded polystyrene or the plastics from Europe, the European building trades, found its way over into the U.S. market. The combination of the two created the very first SIPs that were laminated in the laboratory up in Madison, Wisconsin. As I said before, the SIP contains three components: the skin, the core, and the structural adhesive. A SIP has often been compared in strength to a steel I-beam. The skins act as the flange and the foam core act as the web. And by virtue of the structural adhesive holding it together as a composite panel, in order for it to bend, one of the skins is in compression and the other is in tension, and it gives it a great deal of transverse strength. As you can see in the picture, we also have optional electrical chases. We'll talk about that later in the program. There are many different types of SIPs. In this view, you'll see that insulated metal wall panels can be manufactured. They are often used as exterior cladding and will, in most cases, not carry axial loads. Most of the times you see metal skin panels being used, they are put over top of a pre-engineered metal building. So for instance, if a large cooler freezer building or something of that nature is being built, it'll typically be a red iron or a steel structure, and then the panels are attached merely as cladding. And with the metal skin on the face of it, that gives you a finished siding appearance or a finished cladding appearance, with all of the benefits of the foam core, so you get the benefits of the thermal performance of this type of panel. In addition, another type of SIP might be one that uses a cementitious board or even an MgO, MgO being magnesium oxide. MgO has come on quite strong lately in the SIP industry in the last 10 years. The magnesium oxide board has a lot of benefits, as does cementitious board. But in both cases, they also have detriments. They don't have nearly the testing, the code approval. In some cases, they can be more difficult to work with. In some cases, they're more difficult to cut, or in fact, they create a heavier panel. All things have pros and cons, and MgO board and cement board and metal skins and other types of hybrid skins are no exception. Understanding what those pros and cons are is key to understanding how best to design the building and how best to specify which type of panel is going to be used most predominantly. The panel that, without question, is what we would consider the standard or ubiquitous panel within the U.S. or North America is going to be the 7/16 wood-skinned panel, but it's certainly not the only one that can be used. Now, to further understand what a SIP is, it is not a pre-insulated stud wall. It's not the type of framed walls that show up either with or without insulation such that they get put in place. A SIP has a solid core. It replaces the wall studs and provides much higher thermal performance by providing a whole wall R value that is greater, substantially greater, than an equal thickness stud framed wall. It eliminates all the thermal bridges. It has continuous insulation, so therefore we have the ability to improve the thermal performance, but not just that, we also can improve the carrying capacity. The idea is to use the OSB as the load-bearing element as opposed to using those studs. And this gives you a bearing area that is substantially capable of carrying greater loads. As a designer, one must select various types of connection detailing. When we talk about SIP basics, an in-plane joint, whether it be a wall or roof, this is one of those very standard details that you might see. On the top left, you see what was referred to as a surface spline joint. The foam is recessed and or finished in the manufacturing facility to allow the acceptance or to receive the surface splines that are then put in along with either mastic or expanding foam and nailed off on either side of the panel, either side of the joint, to bring the panel joint together and give you a continuous structural component. One of the beautiful things that we like to point out with the surface spline connection is that the foam is continuous. There is no break. Similar to the surface spline detail on the left, if we look to the right, we see what is often referred to as a block spline. And the block spline also is sometimes referred to as just a mini SIP. It's a SIP where the splines are laminated to the foam core and they fit into the edge of the panel where the foam has been relieved to allow that miniature spline or block spline, if you will, to slide in. Once it's sealed, it can be sealed with mastic or foam. It can also be nailed off on both sides and give you the exact same finished result. Whether the surface spline or the block spline is used is really a function of how the manufacturer has set up their operation in terms of treating the edges of the foam or the edges of the panels such that they use or rely on a surface spline or a block spline. Either one of these details is free of any thermal bridging, which gives you one, a greater thermal performance because a lack of heat transfer at the joints, and it also is an easier joint to seal to reduce air infiltration or exfiltration. And when building with SIPs and installing the panels in the field, stopping air infiltration and exfiltration is really key to optimum performance of a SIP system. One of the other SIP basics that you need to understand is R values, and R values can be a very tricky thing. First and foremost, let's look at the chart, and let's look all the way at the bottom at one of the notes. R values are determined or marketed at the mean temperature of 75 degrees Fahrenheit. We choose this temperature because foams will perform differently as the temperature either increases or decreases. The other thing that some foams will do is they will stabilize at an R value differently than they are initially manufactured at. So hence the term aged R value is also important. Understanding both of these factors sometimes explain why manufacturers' claims of R values can seemingly be either higher or lower with no apparent explanation. This chart gives true and fair R values that can be utilized when comparing the different types of cores. The EPS core, for instance, in a 6.5-inch panel is at around 21.6 as the R value. If we move to an XPS, it jumps up to 29.5 and all the way up to 32.9 or rounded to 33 if you're in a polyurethane core. Understanding this is key to delivering the thermal performance that's required for your structure. Also, understanding this is key when you start considering whether or not you are matching or meeting the code requirements as it relates to either prescriptive method or performance method, keeping in mind that there's more than one way to become compliant with the model energy code, and the R values are a big part of that. Another one of the basic details shown here on the screen is that what you might see in a corner. If we've got two wall planes and they need to come together, we need to attach the two. The different types of screws that are provided and made available by the SIP manufacturers within SIPA is screws that penetrate wood. We also have self-tapping for light duty as well as heavy duty compliance. This will allow us to take a SIP. The screw tip on the far right you see will self-tap into mild red iron all the way up to 3/16 of an inch thick. So we can attach directly to a steel structure. In the detail you see the top panel runs long, the vertical panel in the diagram is actually running short, and the connection of the two is a function of the SIP screw which penetrates into the shorter panel and pulls the joint together tightly. This joint is sealed by virtue of either a foam or a mastic that again stops air infiltration from either moving in or out through that corner detail. Mastic, again, being probably a most commonly used sealing methodology when it's a wood-to-wood connection. One of the things I often see in commercial structures is the use of engineers in the design process who are not familiar with SIPS and tend to fall back on what they know and not what they need to know as it relates to SIP and SIP construction. This will often result in buildings being over-engineered, which drives the cost up. This is especially important in commercial buildings and hybrid systems such as SIPS with steel. Understanding how the SIPs can work, how they will provide structural support and structural stiffness to a building is key to understanding not only the design of the joints, but the fastening, the number of fasteners, how they are specified, and how the entire system is going to hold together and deliver that which is needed and not be over-designed and run costs up unnecessarily. Design professionals, engineers included, have the ability to use charts which are available from SIPA manufacturing members, and these charts will deliver all kinds of data that help determine the best design and the best detailing to deliver the proper performance. In this case, we have a chart that shows allowable axial loads, which will help determine the appropriate wall thickness. In this case, the engineer can use this chart to determine which panel thickness will be required based on the allowable loads that's going to be put on a specific wall. In this case, the chart references transverse design load. Here we have transverse design loads for walls and roof, and this helps determine what the span and or the spacing of the structural elements are within a structure. Not only the thickness of the panel, but based on that span and the deflection, or the allowable deflection, will determine what the overall loading of that panel will carry based on the span. As the engineer or the designer considers shear wall performance, this chart will help determine what total shear wall assembly requirements are based on the edge members and how those members are fastened or attached, both on plates and end studs, what those shear wall connectors are, either nails or screws, and or the requirement of hold downs as it relates to anchors into the decking or into the concrete slab, whatever is required. In this case, we see a variety of different hold downs that work in conjunction with SIPs very nicely. In some cases, the straps which attach to what would normally be considered attaching to the studs, in this case, may have to attach to dimensional lumber, which is inside of the panel joint. So as the panel design is completed, understanding what those racking and or shear requirements are will determine what types and how many hold downs or anchors are required. And in that shear wall, it may be required that additional panel joints with dimensional lumbers at that joint connection allow these anchors to be appropriately attached such that we can deliver the amount of resistance required for that shear wall. The values provided for shear walls are available to cover the seismic design categories. In addition to diaphragm values for the wind or transverse wind loads on the design for both SIP roof panels and walls, these are all available from the manufacturer. And in all shear wall examples and diaphragms, the chord forces are critical. The manufacturers will provide and have the data that shows how straps can help transfer these forces across joints, especially those joints where we have lumber inserted, as we talked about in the earlier slide, where lumber joints may be required for proper attachment of hold-down anchors. One of the often asked questions about structural insulated panels is headers, and do I in fact need headers? And there are some simple rules of thumb, but what it really comes down to is how wide is an opening and how much material is above it. And ultimately, do I have a point load above that opening? And this will determine whether the requirement of a structural header is needed. In many cases, with a uniform load, a fairly narrow opening, and a significant amount of SIP panel left above that opening, the panel, by virtue of the fact that it is structural, has the ability to act as its own header. So when we get into the design, one might suggest that you could eliminate cost, speed construction, and improve the thermal performance merely by making your openings somewhat smaller, or keeping enough material above those openings such that the panel has the ability to act as its own header. The manufacturers have the charts which allow the designer, the design professional, or the engineer to determine whether or not, in any specific example, if a standalone header is required or if the panel can act as its own header. Now, talking about fire ratings with SIPs, we must think of a SIP as a rated assembly, much like any other wall assembly. And a rated assembly is tested just as an assembly, not its individual components. Because the SIP is made out of wood, it has various restrictions that we must consider. We have to think of the assembly and not just as the parts. Insulation or even wood is flammable, and so are many of the parts of an assembly. Therefore, we layer on different components to get the type of rating that is desirable, and that's how SIPs create a fire-rated assembly. In this case, you'll note that the assembly over top of a 4.5-inch standard SIP, we apply 2 layers of 5/8-inch gypsum wallboard to create the 1-hour rated assembly. Different types of fire-rated assemblies can be seen in this slide. On the left, you'll note that we still have a 1-hour assembly, but here the different type of spline detail is shown. This, of course, is the double-dimensional lumber spline with the same types of layering over top, only in this case we're with a single layer of 5/8 gypsum wallboard, and again we're seeing a 1-hour assembly here. We move to the right, we see a 1-hour rated assembly only on one side of the panel, where we're applying 2 layers of the 5/8 gypsum wallboard to the inside, and of course the beam required to provide the structural support, and again we note that we have a 1-hour rated fire assembly. If we move away from fire and we start talking about sound, we have to consider how SIPs perform in blocking or absorbing sound. This can be fairly complex. The sound transmission class, or the number that defines what the rating of that assembly is a function of how the sound is absorbed or passes through that. An STC rating wall assembly for SIPs have been tested and are similar to stud framing systems in terms of values. The SIP walls also perform very well with high frequency or low energy noises. Where they tend to fall down is where we have very low frequency and high energy noises, where then the SIP acts as a diaphragm, which of course it is, and it can transfer that low, heavy beating or thumping noise through to the inside. And this is where we have to add additional layers to get the type of STC numbers that we want. If we look to the slide to the right, you'll notice that the STC number has now jumped to 33, substantially increased over the slide on the left, and this is because we've attached gypsum wallboard to both sides of the assembly. One layer of 5/8 gypsum wallboard adds a lot of mass, and of course mass helps the STC number or the sound performance go up substantially. In this case, we're up to an STC of 33, still a single wall assembly. Still working with sound transmission class, we look at 2 double wall assemblies. The one on the left has an STC number of 45, and we achieve this by not only using 2 layers of SIPs, but also with a 1-inch air gap between the two, and of course 5/8-inch gypsum wallboard applied to either side of both of the wall SIPs. In this case, the STC 405 gets us up fairly high, and we can even go higher than that by applying double layers of 5/8 gypsum wallboard. Here, in fact, what we're doing is we're adding mass, and the density of this mass is what helps knock down these higher energy, low frequency sounds. One thing that we have noted over the years is that SIPs, even though in some areas the STC number seems to be relatively low, is that it must always be considered that a lot of sound travels through assemblies by virtue of cracks or holes in the wall assemblies. When you have a leaky assembly that leaks air, it also leaks sound. So sound that travels on air doesn't get into an airtight structure. Whereas if we make that structure airtight, the only way that sound gets through is by virtue of the fact that it goes through the wall assembly, and this is why the low energy, high frequency sounds tend to cause our STC numbers in the SIP environment to drop quite substantially. Adding that mass and making an airtight assembly will create a very soundproof assembly, and one that clients have time and again told us that SIP houses perform very well when it comes to soundproofing. This building, located in New York, is an example of SIPs in metal framing as well as structural steel. It uses a 6.5-inch wall panel. When I say 6.5, it typically means a 5.5-inch core, which will accommodate a 2x6 dimensional lumber inside between the skins, so we call it a 6.5-inch panel, and a 10.25-inch roof panel. The panels are over top of structural steel beams. The beams are separated by 18 feet, so you got an 18-foot span on the roof panels, and inside the panels, the SIPs are spanning from beam to beam, and they have a structural I-beam, wood I-beam, as the joint, in-plane joint connection on 4-foot centers that help allow that roof panel to carry that large span. This commercial structure, a middle school located in Illinois, uses a 6.5-inch wall. There are some 8.25, but predominantly it's a 6.5-inch wall panel that provide the wall assembly outside of a steel post and beam structure, if you will. Over top of the steel I-joist, we have a 10.25-inch roof panel. So again, we're using basically a steel frame to help carry all those gravity loads, and then the panels are laid over top and attached to that steel structure. These are two different pictures of the same middle school located in Illinois. On this particular project, SIPs were chosen because they were deemed to be the most cost-effective system that was considered in this particular project. If we think about SIPs on the roof for just a second, one can consider the structural nature of the panel and the fact that it can span greater distances. Not only can it span those distances, which in some cases allow us to remove a significant amount of steel to help lower the cost and make the building lighter, but also the panel, by virtue of the fact that it's a continuous diaphragm, allows for the bracing or a reduction in some of the bracing, cross bracing, that you would typically see in a steel structure. The roof itself is acting as a giant diaphragm or a giant brace on top of that steel I-joist. The success of this building is really a function of the coordination of both the architect, the structural engineer, the SIP engineer, the SIP manufacturer, and even the installer of the SIPs. All these people must work together in order to guarantee the success of the project, such that everybody knows what is being done, how it's being done, what the details are, and how the building is going to be put together. This commercial structure, again, is a steel superstructure. This is actually a manufacturing plant. It's a SIP manufacturing plant located in Cottonwood, Minnesota. The design of this building utilizes a 6.5-inch wall panel, which you can see being hung and placed into position in the picture on your left, where it's being dropped in and then attached directly to the steel purlin beams, which are part of the steel superstructure. The roof was all 10.25-inch panel, and again, I point out the fact that the purlins, or the roof beams, are spaced wider than you would normally see in a building of this type and size located in Minnesota, where the snow loads are substantial. And the reason they're doing this is because the panels have the ability to create some of that span. So you're still handling all the loads, you're just doing it a little bit differently. And while you do that, you have the ability to reduce some of the steel costs, which lowers your overall cost of your structure. This building has an unbelievably low heating bill throughout the entire winter, and they save hundreds instead of thousands of dollars a month during the winter by virtue of the fact that their heating bill is so low. I mentioned timber frames earlier. SIPs and timber frames are a natural fit. We sometimes will say it's the technology of today over the old world craftsmanship of yesteryear. In this case, you'll see the traditional mortise and timber framing, and then the panels wrap that frame. And when they do wrap the frame, they actually give that frame an unbelievable amount of stability and bracing where the panels can act as a shear wall. Now, if we look at this big gable wall with all the windows on it, I would suggest that, yeah, that's not necessarily going to provide all of the shear just by virtue of the panels because of all of the openings. So there's some real engineering that has to go into this design, one for the gravity loads of those beams which penetrate the structure, and underneath that there's going to be posting all the way down. But the timber frame and SIPS provide beautiful structures. They are relatively easy to work with, easy to build, and having panels that are as large as 8 by 24 means that we can cover a frame up very, very quickly. And of course, attaching to the wood beams and posts and purlins is very easy for a SIP installer. Here you can see various glue lams with structural steel connectors. This provides for a very interesting look, and with all of that wood in there, certainly the attachment of the SIP wall and roof panels is very, very easy. It's a very nice design, and again, it allows the architect or the designer a lot of latitude on what the building is going to look like and still providing optimum performance. One of the concerns we always have as we move into design is code compliance. And as the compliance for the Model Energy Code increases, as we have seen both in the 2012 and the 2015 codes, the need for or the use of continuous insulation provides a significant benefit, a higher R value, and of course airtightness becomes a very key element in code compliance as the Model Energy Code increases even more and more. The 2012 has seen a 13% increase in efficiency over the 09 and 30% more efficient than the 06. So these insulation requirements in the building envelope continue to increase, and SIPs in every way, shape, and form, I will say, easily allow compliance with the code as it relates to delivering a airtight continuous insulation envelope. A key element of code compliance, and even more so than code compliance, is the detailing, is to fully understand the Iecc climate zones. The climate zones are broken into moist, marine, and dry, and they, of course, in the lower 48 go from 1 to 7. Depending upon where you're designing, very clearly should dictate how your design addresses the movement of heat or addresses the movement of humidity within that structure. And your design detailing very clearly should take the location you're building into effect. We don't design buildings for Florida the same way we design buildings for Minnesota, because they don't work. The building science rules must be strictly adhered to in this situation. One of the things that many designers often overlook, and certainly owners and builders overlook, is the fact that there is more than one way to be in compliance with the Model Energy Code. The one that is overwhelmingly used and understood is, of course, the prescriptive method. Here is the chart showing the requirements for R value for the 2012 IEC Commercial Code as it relates to the prescriptive methodology. Now, the prescriptive methodology just pulls out an R value and says, for this type of structure in this orientation of this type of assembly, the R value must be X. We switch to this very next chart, and here we see the 2015 IECC commercial R value requirements. Again, a prescriptive requirement. It's not looking at the performance method or the substitution method. It's just saying, okay, if you want to comply via the prescriptive method, here's the minimum R value that you need. Before we look at the other methodology of code compliance, i.e. the performance method, let's talk about why that might be beneficial. If we go to the Oak Ridge National Labs and we look at their studies that they've done on SIPs, they break down what continuous insulation, no thermal bridging, and how that affects the overall R value. If we look at the R value of just the insulation, for instance, in a wall insulated with batten insulation, we're again just looking at the insulation, and it might be an R13 or an R24 or R30, whatever that might be. That doesn't take into consideration the framing factor or how much stick framing there is in that wall. If we look at the SIP, where the framing factor is infinitely lower, we have what the code allows us to refer to as continuous insulation. By having greater amounts of insulation, and on top of that, far less air infiltration and exfiltration. We can see in this chart that was part of Oak Ridge's study is that a 4.5-inch SIP, pictured on the far left, had an R value in whole wall performance actually greater than the 2x6 stud wall, 2x6 studs at 24-inch centers, with a quality installation, meaning the batten installation was installed properly per the manufacturer's recommendation. So even in this case, although the rated R value is actually less than the 2x6 stud wall, in whole wall R value performance, you'll see that the 4-inch SIP outperforms the 2x6 batten insulated wall. Very interesting when you consider how assemblies truly perform more so than what the rated R value is. And of course, if you do not believe the whole concept of thermal bridging, all it takes is a little thermography to look at a wall when it's warm on one side and colder on the other, and you can very quickly see how it is that thermal bridging, or the transfer of that thermal energy through any solid lumber components inside that wall, will very quickly rob your building of optimum thermal performance. The picture on your right very clearly shows without any studs in place. Again, good design, good engineering, eliminating as much of that lumber as possible to let the panel do all the work and create a highly airtight, optimal thermal performance structure. Okay, let's get back to code compliance as it relates to the performance method. In the performance method, we don't necessarily look at a line in the sand for a particular R value and say that meets the prescriptive method, or that meets the value required by the code. We look at the entire building, and in that whole building, we model the building using a number of, or any one of many different types of software packages, basically doing a manual J calculation and determining what the overall BTU heating and cooling requirements are. And when we do this, we take into consideration air tightness, and the air tightness has a huge influence on the overall performance of a building. And therefore, the performance method allows us to show code compliance when the prescriptive method might suggest that that very same building is not compliant with the code. And of course, showing this code compliant means that in many jurisdictions, the code official will require that ComCheck or other approved software is used to verify that that meets the code. One of the other issues that often comes up is the idea of Energy Star commercial tax credits or tax deductions. And in this case, Energy Star currently provides credits or tax deductions which equate to $1.80 per square foot. And this assumes a certain performance level of the building. So using the approved energy modeling software to show that the building performs at a certain level, this will show code compliance and perhaps allow for commercial tax credits. Now, in order to get all of the optimum performance and the tax credits and all those other things that both you as the designer and the owner of the structure, owner of the building want, requires proper installation. And installation is really a very, very key component of the success of your design and your building. In order to get good installation, we have to always be addressing air tightness. Not only do we have to hire somebody and specify somebody that knows how to install panels, but there should be a methodology to prove and verify that the air tightness is in fact being delivered by good installation. When the installers of panels are working in the field, they have a number of methods by which they can create an airtight joint. It might be a gasket, it might be an injected foam, single component or two component foam, it might be mastics or tapes, and all of these details are largely driven by the manufacturer that is being used, and this will dictate how the installer uses these components to deliver a very airtight, high-performing assembly. Many of you may be familiar with the architectural challenge known as the 2030, which can be found at architecture2030.org. And this is a challenge to architects and design professionals to improve our built environment. It is a movement towards the reduction of carbon emissions and eventually to meet the carbon neutrality for the building industry in 2050. 30. And it's based on the idea that we can build buildings with greater insulation, greater continuity of insulation, as well as air tightness and reduced infiltration, things that I've all talked about before, and of course reducing the construction waste so that all of our buildings are more gentle on our environment and will deliver higher performance for this carbon neutrality for all of the buildings by 2030. We touched on life cycle analysis earlier, and basically, as you probably well know, the life cycle analysis looks at the manufacturing of a product all the way from the very beginning of its sourcing its raw materials all the way through construction, and then its how much energy it consumes over its life. In essence, what we're doing is we're saying we use a lot of energy to mine and produce the materials, the natural resources that are used to build a SIP, and that might be higher than other forms of construction. But then once the project is built, we're saving energy substantially more so than over to-buy construction. So what happens? Well, over a certain number of years, we start seeing a payback in that we are saving more energy than we ever used to produce those components. The EPS Molders Association's analysis shows that within climate zones 1 through 5, you're seeing an average payback of about 5.1 years, and that is even a little bit lower in terms of recapturing the greenhouse gas emissions. Again, zones 1 through 5. If we go to the higher zones, it happens even quicker because we're saving more energy comparatively in the colder climates. Other analysis have been done both by BASF and the Oregon Department of Environmental Quality. The BASF study showed that the SIPs outperformed 2-by construction for a life cycle analysis, as well as the Oregon Department study showed that the SIPs reduced on-site construction waste when compared to other types of systems. Continuing on with our discussion about life cycle analysis, we can drill down into some of the finer details in this U.S. model. If we look at the top and we start talking about energy savings, SIPs versus stud wall, you can see the energy investment in millions of BTUs for a single-family home built in the U.S. A SIP consumes about 177 million BTUs, whereas the stud frame walls only 110 million BTUs. So right out of the gate, one might make the assumption that, well, I'm far better off from a life cycle analysis or an energy standpoint to build with stud frame walls because they don't use as much energy to create. As we look down further in the chart, we go right down to payback period in years, average again 5.1 years before the energy comparison between SIPs and the stud walls shows that the life cycle analysis of SIPs creates an overall decrease in the total amount of BTUs required to build this single-family U.S. house or single-family structure in the U.S. And then if we drop down to global warming potential reductions, we again see that comparing the SIP and the stud wall, you have difference in terms of tons of CO2. The SIP appears to be greater, but then as the structure is lived in and the savings compared to the stud wall, you get an overall comparison of a payback of about 3.8 years before you're starting to see the savings in CO2. And of course, if you look at the savings over 50 years, you see almost 50 tons of CO2 being saved over that equal stud frame wall. We've touched the idea on thermal bridging, and this analysis, often done by a WUFI, is a section view of the wall or roof assembly, and it shows the varying degrees of temperature or the temperature variances. The SIP wall assembly on top shows that we have a relatively uniform temperature gradient lines. The outside or the top skin might be colder, the inside or the lower skin might be warmer, and the two don't come in contact. Why we want to look at this is because we're concerned about any water vapor or moisture within the assembly. Will it ever condense? So if we have any leaks or any movement of air in that assembly, if that warm, moist air comes in contact with a cold outside skin, we have condensation, and condensation leads to mold and rot and mildew and eventually loiters, and we don't want any of that. So the WUFI analysis of the SIP structure shows a nice clean straight lines of temperature gradients, whereas the gradient of a stud frame wall, where the stud acts as a thermal bridge, we get the movement of that cold the energy loss through that stud, and it creates a cold spot in the wall, and that cold spot provides an opportunity for condensation and ultimately moisture problems. We talked earlier about climate zones, and here we're talking about climate-specific design as it relates to various areas in the country where we have more or less moisture that we have to address. If we live in an area of the country where we get a lot of moisture, the detailing must be different. We do this because of the durability of the structure. This is not a SIP-specific issue. This is any building issue. Where it rains more, we must allow for the drying potential of that building. Special consideration should be made for the designing with SIPs in cold and wet climates. And it's done to prevent erosion as well as mold growth, which imparts poor indoor air quality and create hazardous environments for the indoor occupants. With water intrusion, the bulk water and liquid moisture from the outside coming in is done so through wind and driven rain. You must know what climate you are building in order to effectively able to be putting the proper detailing on your drawings to address not only bulk water, but air infiltration as well as vapor drive. We start talking about climate-specific designs, and the idea of building science really comes into play. I'm a huge proponent of back ventilation or drying. SIP structures and other high-performance, low-energy buildings automatically have a lower capacity to dry because they don't have a lot of energy or heat moving through the assemblies to help them dry out. Because they don't have a higher capacity to dry, we need to promote within our design additional opportunities for those buildings to dry. In both of the pictures you see here, what the designer has done is to create drainage planes or a rain screen to allow for that drying of the SIPs to the exterior. We don't want to trap that moisture in. We want to be able to let it get out. Consider Murphy's Law in that moisture is always going to get into your assembly. In one way or another, it's going to get in. So your job is to create a methodology for it to get out. Easily and quickly, your assemblies should be able to dry. Whether you use a drainage mat or furring strips, whatever your strategy is based on the climate zone that you're building in and the amount of water and vapor that you need to address should determine how robust a drying opportunity you give your building to lose that moisture and dry out on whichever side the system has to dry. As we look at the cladding of your structure, regardless of whether that cladding is wall or roof, we need to consider what is the appropriate method to drain that moisture away. Roofing paper is an acceptable means to help dry or help create a drainage plane under your cladding. In this case, it might be shingles, to move that moisture down and away from your building. If you're in the colder weather or the wetter weather, then perhaps not just roofing paper, but again, we go to back ventilation where we build a second layer of roofing or we use some type of ventilation matting to provide for the movement of more air under that cladding to help dry things out. In some cases, standing seam metal roof. It's a wonderful roof cladding, but in the right environment where we run the risk of additional moisture being trapped underneath that metal, then perhaps a ventilation mat is required to help increase the durability of that structure. Now, if that metal wasn't standing seam but was a multi-crimped metal, well, you have a self-ventilating cladding. Key element is always to look at what type of cladding you're dealing with. If that cladding is self-ventilating, it's got a built-in methodology of promoting drying. So in some cases, in climates where I'm worried about moisture, I will automatically look to claddings that are in fact self-ventilating. For instance, a tile, a multi-crimped metal roof, some types of sidings which allow for air to move behind them. Some of the shakes or the shingles that have an attachment such that it creates airflow behind the cladding itself. I want to talk briefly about indoor air quality as it relates to SIPs, and given the fact that they use OSB as their standard sheathing. The OSB of old used a urea resin in their binders, which provided for formaldehyde in the product. Today's OSB is produced with a phenolic resin, and the amount of formaldehyde is absolutely negligible. We can easily show compliance by using the product standard, which is a PS1 or PS2, low emission levels, which are compliant with both HUD manufacturing, California's CARB ratings, as well as Japanese and European standards for formaldehyde. In essence, formaldehyde is virtually a non-issue as it relates to SIPS when using OSB. The amount of formaldehyde that you will see in testing is below the amount of formaldehyde that you will be exposed to if you were to be outside in the natural environment. As the designer, there are many things that you must pay attention to during the design phase to ensure the successful outcome of your structure. Coordination in all areas may need to be rethought when considering a SIP structure. For instance, HVAC. Who's doing the sizing of the HVAC system? What is the actual tonnage based on the low energy consumption of this building? In most cases, rules of thumb will absolutely put you in the wrong size system and must be avoided at all costs. So proper design and size equipment has to be taken into consideration, as well as window and door openings. Electrical. Somebody needs to talk about electrical runs requirements such that the owner's requirements, the need for electrical, is addressed by the design of the panel drawings, and the manufacturer has the ability to put electrical chases where required. The structural system, coordinating the steel and the concrete so that we have the appropriate support and the tolerance of those support systems such that the SIP system works appropriately on this. Coordination with the SIP manufacturer is going to be key, as well as the installer of those SIPs, so everybody again is on the same sheet of music and the success of the building is ensured because of proper planning. Talking more about SIPS electrical or the electrical systems within a structural insulated panel, wall, or roof, very easily addressed by the manufacturers having developed standardized wire chases which are placed inside of wall and roof panels, either horizontally or vertically, to allow for the standard movement of wiring through the panels for easy connections, either connections around walls from floor to floor, or as well as into any box or lighting box for the electrician to make those connections. We have standard heights. Those can be removed, they can be added. Holes and SIPs can be provided by the manufacturer to allow for any of these mechanical system runs, specifically electrical, and you can also impart or request additional wire chases if, for instance, you had a sconce light and you needed a horizontal wire chase at the 6'2" level off of the floor. It can be done. It just needs to be discussed. It needs to be coordinated with the manufacturer, so when the panels are delivered, they are in the configuration that makes your building a success. Specifications are incredibly important, assuming that they're going to be followed on your particular project. This allows you to specify types of panels, as well as the very specific things like installers that are required for this particular building. You can find specifications certainly at the Structural Insulated Panel Association's website at sips.org. You might also find those boilerplate specifications on the particular manufacturer. They provide those specifications. Of course, those manufacturer specifications are going to predominantly put a specification out there that promotes one particular type of SIP, which is the one that they produce. So more generic in some cases might be more beneficial for your particular project. The one area of specification that I am going to harp on specifically is the next one. In this case, the specification looks at quality assurance, and this is where I harp a lot on specifications for people that I consult with, and that is not only should the SIP manufacturer be a SIP Association member, and I say that because all manufacturers of SIPA meet strict compliance for quality assurance, meaning that they have testing, they have code approvals, and they have third-party inspections of their facilities to ensure that a quality panel is being produced and delivered to your job site. So the specification of a SIPA member manufacturer, I think, is very important. When it comes to structural design, I think that a professional engineer in all commercial buildings, with almost without exception, is required, such that we're working with an engineer who understands SIPs, and you're going to get the best bang for your buck out of that SIP structure. And C on quality assurance might be the most important one you'll find, and that is your installation contractor. If you let a standard framing crew that has no experience and no training install the SIP package, you run the risk of having a structure not perform the way it should, or small issues that might crop up with an unqualified installer may lead to bigger problems because they don't know how to address them because they've never received the training. Having a lead installer or a supervisor that has a minimum number of years of experience is great, and that's all fine and well, but just because they've been doing it for 3 years doesn't mean that they've ever been properly trained. One that has some level of certification or one that has passed some type of curriculum, I think, is going to be the best bang for your buck, and that's one specification I absolutely would encourage you not to allow be broken. Put somebody on site that understands SIPs, has put them up, and can show that they've put them up successfully. Nothing worse than having a wonderful building and a perfectly good SIP package delivered to a job site only to see it improperly installed by an unqualified crew. Certainly the SIPs have benefits when it comes to construction. Some of those benefits outlined here above. There's many examples of a four-man crew installing all of the wall panels on a 4,000 square foot home on a single day. It can be done. They go up much quicker. This also assumes that the panels have been properly designed. They have been fabricated in the manufacturer's facility and delivered to the job site ready to assemble. You will in some cases hear the term ready to assemble or ready to install, and this basically means that the panels are just that. They're ready to start standing up as soon as they get to the job site. If you were to deliver a truckload of blank panels, you might think, well, gee, I'm saving a lot of money on my panels, but you have destroyed the opportunity to increase the close-in or the dry-in time, because now the installer or the trades on site need to start cutting panels on site. You've lost all the benefit of a structural insulated panel by doing that. Take advantage of the CAD design and the CNC fabrication capabilities of a SIPA manufacturer and have a package delivered to your job site that's ready to put up quicker. Other areas that you'll save time, of course, going to be other trades can move quicker. Some people would suggest the electrician may or may not be able to move quicker, and that's a function, again, of whether or not your installer has taken the precaution to properly notate the panels, pre-drill the panels, and think about how the electrician needs to move through that wall assembly or roof assembly, such that when the electrician does show up, he's not standing there scratching his head going, well, I don't know how to get from point A to B. The SIP installer and the design precautions that were taken ahead of time ensure that the electrician can move very quickly through that particular project. SIP job sites will have less waste. Everything will typically be stronger, straighter, and truer because of the nature of SIPs and how they go together. Different commercial applications include any type of commercial building that is of a type that does not require zero combustibility of the products. There's very few commercial buildings that cannot be produced out of SIPs. This is just a short list of many of those that we often see built with SIPs successfully around the world. This is a couple of photos of the Rocky Mountain Institute Innovation Center in Colorado. It was built to the Passive House standard. It was certified, which means, of course, it had air infiltration of less than 0.6. In this case, you can see it came in at 0.36 air changes per hour. And it has 83K of photovoltaic applied to it. It produces, I believe, about 2 to 3 times the amount of energy it consumes. It is considered to be one of the most energy efficient structures in the United States. And it uses a lot of timber in that project. It also used some curved SIPs. One of the beauties of structural insulated panels is they can actually be manufactured with a curve in them. So it provides for some interesting design detailing. This elementary school was built in Las Vegas. It saved almost $1 million in the direct construction costs as a function of using SIPS. It knocked somewhere in the neighborhood of about 45 days off of the framing schedule by virtue of the fact that the panels came in pre-manufactured and they were able to put them up. This school is still seeing a reduced lower heating and cooling bill with the capital savings as a function of the proper HVAC design. There was a substantial amount of reduced waste, which resulted in reduced disposal fees and, of course, the environmental impact therein. They also enjoyed benefits with the fact that they were close to Nellis Air Force Base. They actually had reduced interior air noise, and that was a function of being nice and airtight, and so they didn't have a lot of that airport traffic noise coming into the classrooms. Here's another shot of the same school, both the interior courtyard with some of the design elements that were incorporated in the building, and to the left you can see where the large thick roof panels were being laid down over top of glue lamp beams, and the installers are preparing to attach that panel that you see on the left photo. This particular commercial project was a 3-story assisted living facility, a 48-room, all SIP construction project located in Minnesota. Nothing like keeping retirees and the elderly warm, and nothing better to do that in than a all SIP project. There was estimated to be a 30% reduction in greenhouse gas emissions and dramatically reduced the cost of heating, specifically heating this building in the Minnesota winters. Here we are at a junior high school in Kirkland, Washington. You can see the SIPs are laid over top of a glue lamp beams. This commercial structure again enjoyed huge reduction in energy consumption through cost-effective mechanical systems. They had a reduction in labor by virtue of the SIPs installation, and because they saved a lot in the labor costs, they were able to purchase the PV system and kept the project on budget. It was one of the things that was attributed to the ability to keep the project on budget. The reduced heating and cooling consumption was critical for the building to achieve net zero energy ready design, meaning that the potential for the roof mounted solar panels was going to allow this overall commercial project to go to net zero energy. And for a commercial junior high school building, that's quite an achievement. And here are some outside shots of the Kirkland, Washington Junior High School with some very nice shots of what the building looks like on the outside as it's finished. It's open, it's airy, it's light, it's got lots of windows in it. It uses a 6-inch thick wall and a 10-inch thick SIP roof panel, and it was designed to be 47% more energy efficient than the baseline target for schools in that area. This is a wonderful project. I say that because, again, up in Minnesota, here we are dealing with a 4-story all SIP structure. So people will often ask, well, how high can I build with SIPs? And this is a perfect example with good design and good structural engineering. The manufacturer, Extreme Panel Technologies, up in Cottonwood, Minnesota, the same ones that built their manufacturing facility out of SIPs on that steel red iron building, they designed and installed this panel package to 4 stories high, and it was an apartment complex that was LEED Platinum qualified. It was affordable housing, and it used 6-inch SIP walls. A continuation of the same project. This is what the project looks like completed. It's been completed for several years now and is nothing but an amazing success for the Minneapolis, Minnesota area. Another example of a very interesting project located in Bend Parks and Recreation in Bend, Oregon. This uses a 10-inch SIP for a rooftop over top of glue lamp beams. This also was a LEED Gold certified structure that was attempting to reduce energy consumption substantially. It also had a green roof on top of that. And here we see that exact same project finished from the front. The 10-inch roof SIPs and the green roof that you can see very clearly in this photo made for actual structural accommodation of the green roof because of the thick nature of the SIP panels and over top the large glue lamp beams. So as we wrap this course up, you as a design professional should now be able to comfortably do a number of things, including discuss the basic of a structural insulated panel, what it is, some of the various types of panels and how the engineering works, codes and standards as it relates to the various types of panels or the basic structural insulated panel. Understand and identify what those energy efficient characteristics are, specifically the air infiltration specifics, and how these help improve the overall building energy efficiency. Understanding the waste reduction as it relates to product life cycle and the benefits of building with SIPS compared to traditional wood framing. Hopefully we understand how SIPS contribute to a better indoor air quality through the reduction of both air infiltration and the interior off-gassing by maintaining good indoor air quality. Also discussing the advanced technical requirements and the design applications of those particular SIPs. Okay, this is my favorite slide because for the next 10 minutes I'll take questions. I guess if you want to ask me a question, you're going to have to do that via email. You can reach me through the association's website, which is www.sips.org. Again, my name's Al Cobb, and I hope you've enjoyed this program. I've certainly enjoyed providing this information and hope that you can take it with you and use it to design better buildings in the future. My final comment as we wrap up this program would be to say, please remember to specify a SIPA manufacturing member so that you can maintain quality and durability in your SIP structure moving forward. I wish you well and good luck designing and building with SIPs.